Welcome, and thank you for joining us for this episode of Let's Talk Water New Mexico. I'm Evan Lamoureux, and along with Liz Jolly, we're going to facilitate the conversation today. This podcast series is put together by the New Mexico Produced Water Research Consortium in an effort to help educate the broader New Mexico population on the topic of treated produced water and the potential that it may have to help water supply challenges in New Mexico and the greater Southwest. The consortium is focused on helping to solve New Mexico water challenges with innovation and collaboration.
As Evan mentioned, I'm Liz Jolly. This is episode 3. We're glad you're with us. And today we're going to be sharing thoughts on the potential uses and applications for treated produced water. As a reminder, in episode 1, we covered the delicate balance between water supply and demand and the challenges with maintaining that balance due to increasing demand and reducing supplies. In episode 2, we introduced treated produced water and discussed a bit about the history. Now that we have set the stage for today's chat, we would like to introduce our special guest. Let's start with Dr. Pei Xu.
Thank you, Liz and Evan, for hosting this podcast series. I'm Pei Xu, a professor in environmental engineering at New Mexico State University. I also serve as the research director of the New Mexico Produced Water Research Consortium. My research is focused on water quality, water reuse, and treatment technologies.
Thanks, Pei. As a New Mexico State graduate, I'm glad to see the involvement of NMSU in this effort. It's awesome to see the participation there. Next, let's introduce Dr. Jeri Graham. Jeri, will you please share a little bit about yourself?
Sure. Hi, Evan and Liz. Thanks for hosting the discussion. I'm a retired scientist from Los Alamos National Laboratory, and I'm currently a research professor at the University of New Mexico Center for Water and the Environment. My research over the years has centered on water quality, water treatment, and the links between energy systems and water use.
Well, thanks, Jeri. Finally, we have Dr. Tzahi Cath. Dr. Cath, will you please introduce yourself?
Thank you for the invitation to participate in this podcast. My name is Tzahi Cath. I'm a professor of environmental science and engineering at the Colorado School of Mines. I'm managing 2 water centers on campus, and in addition, I also have a joint appointment at the National Renewable Energy Lab in Golden. So that allows me to do research in both water and how the energy is connected to treatment of water.
Thank you, Jeri, Tzahi, and Pei for joining us for the discussion today. As we stated earlier, we're going to be discussing the potential uses and application for treated produced water and attempting to tie in the treatment options and the resulting water quality. Starting first with the potential use cases. Jeri, would you share a bit about the use cases and applications that are being evaluated and explored by the consortium?
First, I want to mention that to help solve our ongoing water shortage crisis, particularly in the Western U.S., we need an all-hands-on-deck approach. Using low-quality water, such as produced water, in place of fresh water for industrial uses can conserve our precious freshwater resources for other critical needs, such as drinking water and food crop agriculture. Basically, produced water is unavoidable. We have a lot of it being produced as we extract oil and gas. And so the consortium is working to identify industries and processes where non-fresh water can be most easily purposed. Some of these processes include industrial cooling, industrial process waters, and other systems where fresh water is not necessary and the water is fully contained. So these are significant candidates for this use. The use within the oil and gas industry is already occurring, and that is conserving large volumes of fresh water. Some forms of non-food crop agriculture could also be considered. This might be something such as cotton or hemp that is used for other materials that are not being consumed. There are forms of land applications, such as use in road de-icing or dust suppression, that could be appropriate. However, they do require some careful study for that appropriate use. Mining uses are also possible. Right now, potash mining requires the use of saline water in some processes, and so this is an excellent possible use. Constituents extracted from produced water can include valuable minerals as well, including minerals such as lithium. All these options have advantages and disadvantages. These will need to be thoroughly evaluated, and the quality measurements and treatment selection are thus a really critical part.
As Jeri mentioned, we are looking for the opportunities to free up free water volumes by replacing the demand with treated produced water. This can have a pretty significant impact given the volumes that can be acquired from the oil and gas industry. If we can treat this produced water, that will free up about 10% of freshwater demand from agricultural irrigation.
You can definitely see how this can fit in and be a great solution to some of those challenges that we face in New Mexico.
Now that we've covered the potential uses, I think we need to tie the water quality associated with those various applications. Pei, can you tell us how we ensure that we match the required water quality to the different uses?
Yes, it is very important that we match the required water quality to the different uses. We need to consider several factors, such as understanding the water quality of the raw and treated produced water, and selecting the appropriate treatment processes to meet the water quality requirements of intended uses. Firstly, we need to identify the constituents in raw produced water. Produced water is a byproduct of oil and gas extraction. It typically contains high levels of salts, suspended particles, heavy metals, organic compounds such as volatile and semi-volatile organics, petroleum hydrocarbons, and oil. It may also contain naturally occurring radioactive materials and other inorganic constituents such as hydrogen sulfide and ammonia and the chemical additives added during well treatment. The produced water quality is highly variable. It depends on the basins, formations, locations, and also it changes over time. Secondly, we need to employ an integrated treatment chain to remove all kinds of contaminants and impurities that may affect the quality of the water for intended uses. The treatment processes should be selected based on the intended use of the water. For example, if we use the treated produced water for agricultural irrigation, it needs to be treated to a very high standard than the water used for potash mining or for cooling water used in the power plants. Thirdly, we need to ensure that the treated water quality meets the required standards for its intended use. For example, regulatory agencies set standards for water quality based on its uses, and industries may also have their own specific water quality requirements. We need to comply with these water quality standards through the appropriate treatment processes.
It's interesting to hear about the complexity and the variability of that water quality that's coming back as it's produced. It sounds like a pretty challenging task to make sure that the treatment is delivering the water quality required, given some of those different standards. How do we ultimately ensure that the water is safe for those different applications and meet those standards?
First, we need to have a very good understanding of the water quality. And then we also need to make sure that the treatment technologies we selected have the efficiencies to remove different contaminants. Currently, the New Mexico Produced Water Research Consortium is developing a comprehensive chemical characterization and risk assessment framework for produced water treatment and reuse. Please listen to the next episode on risks and the toxicology assessment of the podcast series. Overall, we need to ensure that the water quality meets the required standards, so the treated water is safe and appropriate for its intended use.
Yeah, matching that quality of the untreated and then the treated produced water to the prospective use will make the water fit for purpose. And Pei is right, this is extremely important. Robust sampling and analysis procedures and then measurement careful measurement of the organic and inorganic constituents has to be performed, and it has to be performed frequently and well. The quality of produced water can change considerably over time and also over location. And these factors have to be evaluated to make the treatment effective. What's fascinating to me is that the treatment trains developed for produced water can also be purposed for other challenging industrial treatment processes. So this is adding considerably to our knowledge of water treatment science and engineering.
Thank you, Pei and Jeri, for going through the water quality and the treatment and helping us understand what is needed to match the quality of the water for the application. Now, Tzahi, can you tell us about how in the oil and gas industry the analysis is done of what's in the water?
Water analysis is not simple. Especially in the oil and gas industry, we have a lot of things at high concentrations. So in order to analyze what's in the water, we are implementing many techniques. Some are very simple, some are very complicated or complex. But in general, once we collect the sample, we have to prepare the sample so that some of the other constituents that's in the sample will not compromise the performance of these machines. But we take these samples and in most cases, we send them to commercial labs where they further process these samples and inject them into very, very expensive machines that have capabilities to analyze water or constituents in water to very, very low concentration, sometimes at the nanogram per liter. This analysis can be expensive, but the unique thing is that in one sample that we inject into a machine like that, we can characterize and quantify the concentration of many, many compounds in the same family of contaminants. So that's one way to analyze what's in the water. Another way to analyze what's in the water is to install special sensors within the pipelines or unit processes, sensors that can detect specific contaminants. Unfortunately, we don't have these sensors for all water quality parameters. But we see more and more unique sensors coming back to the market. And the unique thing about these sensors is that they can measure the specific contaminants that they measure continuously and generate large data sets that can help us understand what's the frequency and occurrence of the different contaminants in the water over long periods of time, and also help us to better improve the treatment processes to operate at the best point where we are completely removing these contaminants from the water. So some of the real-time sensors that we now seeing are unique sensors that use different wavelength of ultraviolet, and they are able to detect different organic compounds, which are the compounds that are especially of concern in the oil and gas industry. But these sensors can do it continuously and therefore help us verify and ensure that the water quality is maintained after treatment.
Tzahi, thanks for talking about ways to analyze what's in the water. Jeri, do you have any thoughts on treatment options to add to the conversation?
Yeah, the treatment options are often based on what we know right now from treating typical wastewaters and typical drinking waters. Usually these are separation processes. We have to separate the water from the constituents that are not desired. Usually we're looking at separations that work to remove groups of chemicals. So we might have separations that are more efficient for organic constituents and separations that are more efficient for inorganic constituents. What's nice is that some treatment technologies are able to treat multiple constituents. We don't just remove one constituent at a time. So we might have different forms of membrane separations. These can use membranes that have very large pores all the way down to very small pores. So we might have microfiltration as an example of filtration with large pores, and that removes larger particles and colloids. We might have nanofiltration that can remove some of the larger inorganic and organic ions and molecules. And then we can have reverse osmosis, which many people are familiar with, and that is able to remove very, very small ions, including sodium chloride, which is a major constituent in produced water. The problem is that the finer the pore, the more expensive it gets and the more energy you have to use.
For the produced water treatment, we need to think about an integrated treatment train. Even though we may implement the desalination technologies such as thermal distillation and the reverse osmosis membranes, but there may be still some small chemicals or compounds that can pass through this treatment process. Then we need to implement a post-treatment to further polish the water quality so the water can meet the reuse standards and also to protect the public health. One example is volatile organic compounds and ammonia in produced water may pass through the thermal distillation process. Then we need to use other treatment processes such as granular activated carbon or air stripping or other technologies to remove these residues in the desalinated water.
It's also important to consider that every time we do a separations process, we have a waste stream that will come out of it. So we also need to be sure to develop appropriate disposal options. And then, of course, we may be able to separate out constituents such as lithium and other valuable metals. Those separations processes are not simple, but they may become very valuable over time as we are using these metals more intensely.
Jeri, in the beginning when you talked, you were mentioning about the treatment train. Can you talk about some of the improvements and innovation when it comes to the full train?
Oh, wow. There's so much that's been going on. It's really impressive. I'd like to, one example would be the use of energy in membrane processes. And there's been various ways to recapture energy throughout the treatment system so that pressurized systems like reverse osmosis or nanofiltration are better able to use the energy that is put in multiple places so that we can reuse pressure, we can reuse that pressure energy and try and conserve the amount of energy used in total. I think Pei has spent a lot of time looking at the order of treatment processes and what is most efficient too. So Pei, can you talk more about that?
Right. Yes. So because there are so many things we can do, how we can put one unit process ahead of others, how we can further improve the treatment efficiency. Yeah, I think we have done a lot of work. Just an example is, should we use granular activated carbon in front of the desalination processes to remove the organics to protect the membranes? Or should we put the granular activated carbon adsorption as a post-treatment process to further remove the residues of the organic carbon in the treated produced water? I think there is a lot of room we can improve. I know this sounds like very cheesy, but it's not very, but basically that's what we do, because if we use granular active carbon in front of the desalination processes, there are a lot of organics that can get the carbon saturated very quickly. Then we need to regenerate the carbon and replace the carbon. It is getting very expensive. But if we put it after the desalination processes, it is less expensive. And on the other hand, we need to think about what are the other treatment processes we need to protect the desalination processes.
Mm-hmm. I think it's fascinating that all of these systems, really, we reuse when we're treating produced water in a challenging environment, challenging water, a lot of constituents in it. we're using technologies that were often originally developed for much less challenging waters. And it's really helping us push the envelope in terms of the amount of energy that we use. We're trying to reduce that considerably, how to order the system so that they're more effective. And so we're not reinventing the wheel completely. We are using known processes. We're not defying the laws of physics. There's only so many ways to separate a molecule of something you don't want from water. And there's a basic amount of energy that's required to do that. But being creative and testing different processes has really helped us have a better outcome. And Pei's and her group's definitely been a large part of this, as has Tzahi and his group.
It sounds like a lot of the optimizations and innovation around treatment is really focused towards increasing efficiency and effectiveness.
It's not very glamorous, certainly. Even a small increment in energy change and in reduction of energy use in these processes can make huge differences because of the amount of volume of water that we're using. So, saving half a kilowatt an hour may not sound like a whole lot, but it can be absolutely enormous in terms of overall processing.
I think that's a great point to tie back to the discussion that we had with Mike Hightower in episode 2, where we talked about some of the challenges with treated produced water and really just the cost associated with the treatment and the transportation. So driving that down is making it a more viable solution for the New Mexico and for the Southwest. It's
all a bunch of trade-offs, absolutely. And it requires really good detailed analysis of the processes and the systems that you're and a good focus on the goals that you're trying to achieve. The fit for purpose water effort is all about meeting a number of different goals and doing it effectively and efficiently.
Yeah, I totally agree with the discussions here. And we know produced water treatment is typically energy intensive and has a high cost. Right now, a lot of research is ongoing to have these new configurations of treatment processes or arrange the treatment systems to make it work more efficiently. And also there are new materials are developing. For example, produced water chemistry is pretty complex. It can cause a severe fouling and scaling of desalination systems. So if we can develop new materials as anti-fouling, anti-scaling processes, this will reduce the treatment cost and improve energy efficiency. Another point I would like to mention is the use of alternative energy sources that can help reduce the environmental impact and the cost of produced water treatment. There are several alternative energy sources that we can use, such as solar energy, including using the PV panels and also solar thermal energy to heat the water for thermal distillation. We can use wind energy and also the waste heat from the flaring gas and compression stations.
So when it comes to treatment of produced water or any other type of water, we look at 3 stages of the processes and 3 families of processes. So the stages is, the first one is pre-treatment. You have to remove some major and maybe I'll say simple constituents from the water in preparation to the core processes, which we call the treatment itself. In the oil and gas industry, it will be desalination, removing salts from the water. But again, it applies also to seawater desalination or other brackish water or surface water treatment. And then after the treatment itself, sometimes we have post-treatment when we need to do small adjustment to water quality, maybe adding back, after desalination, adding back some minerals to the water because it's not healthy to drink water that don't have mineral in them. So these are the stages of treatment. It applies also to the oil and gas industry. Within the treatment processes, practically we invented already all the processes that are they are there, and what we can still do now is improve them and connect them in different ways. But in general, we look at three families of processes: physical processes, which are you can think about filtration or clarification. These are we physically trying to remove things from the water. Then the next family is chemical processes, where we add chemicals to promote some reactions to remove things from the water. Think about adding coagulant in order to remove small particles or organics from water. Think about softening, removing calcium, magnesium from water, or think about chlorination to remove microorganisms from the water. And the third family of processes is biological processes. In general, in wastewater treatment plants, we are taking advantage of the unique capabilities of different groups of microorganisms to remove organic matter and nutrients like nitrogen and phosphorus from the water in order to facilitate the treatment. And so in oil and gas processes, we already use many of these processes in the three steps to bring water from low quality, when it comes from the well, all the way to different applications that we want to use the water for. So that's something that we call fit for purpose. I'll add a small set of processes. I'll reach some water quality that I can use within the oil and gas field. I'll add a few more processes in the train, and I'll be able to improve the water quality all the way to drinking water, or even electronic industry that needs water of quality of much higher than drinking water. But it's possible. Eventually, it's about the cost of treatment and the intended use.
Tzahi, thank you for helping us understand further details about treatment options. Before we wrap up today's episode, let's leave the audience with a few key messages or takeaways. Pei, let's start with you.
Produced water from oil and gas operations is often viewed as a nuisance due to its high levels of contaminants and potential environmental impacts. However, with proper treatment, produced water can be converted into a valuable resource. For example, treated produced water can be used for fit-for-purpose applications to reduce freshwater usage. And also there are valuable elements and chemicals we can extract from the produced water for industrial uses, especially from the concentrate treatment. The benefits of resource recovery can offset the treatment cost and make produced water use more attractive.
I think it's really so important to recognize that despite the amount of energy and complexity of the systems that we would need to reuse produced water, we continue to learn enormous amounts of chemistry and engineering, and how we improve our systems, and also how we put this water to a fit for use purpose. The learning that we've gotten out of examining produced water has really got broader implications for water treatment in general, and for understanding how we can use certain waters in the right ways so that we can conserve our very precious fresh water.
Well, thank you all for being here with us today. This was a very informative discussion that will definitely help our listeners better understand how treated produced water can actually fit into the water supply and demand situation here in New Mexico. And it's clear that there's a wide spectrum of potential uses and applications, but it's also very important to understand that we need to meet the required water quality for each of those uses.
And we hope that you'll join us for our next episode when we cover the human health and safety aspects of utilizing treated produced water. We will be recording our next session at the annual meeting for the Consortium at New Mexico State University. We have a great lineup of professionals from government agencies, academia, and industry. Thank you so much for joining us, and we hope to see you next time.